Wave-particle duality is false in my world. Let me introduce you to the two worlds that we will explore in this video. On the one hand, there is your world on your side of the video screen. This is what we will call reality. On my side of the video screen, we have a different world, one that springs out of my imagination. Now, on your side of the video screen, wave-particle duality is true. On my side, it is false. In order for you to understand where such a crazy idea as this came from, you should know something about me. I am a psychiatrist. For more than 3 decades, I have devoted myself primarily to treating people with chronic and severe schizophrenia, bipolar disorder, borderline personality disorder, those who are addicted to street drugs, people who are suicidal and homicidal and upset. Most of my work has been in a general hospital, in the psychiatry floor of a general hospital, where those who have severe mental illness are at that moment at their worst. If you are the police and you meet someone who's homeless during a snowstorm and that person makes no sense at all, and you ask that person, "Who is your doctor?" chances are they might say, "Why, it's Dr. Jeff Boyd."
We're the staff who work at the General Hospital with Dr. Jeff Boyd.
We've had the privilege of working with him for a number of years and have found it fascinating to work with him. Right now he's going to tell you a little bit more about dual wave oh my God, what is it?
Tracy!
Yeah, but you left me the hard part.
That was on purpose.
He has dual wave particles.
Particle wave duality.
Oh, there you go, particle wave duality.
All right, ready?
Particle wave duality means that you have something that if you look at it one way, it's a particle, and if you look at it a different way, it's a wave. Now, a thumbnail sketch of what I'm about to tell you is that if the particles and waves were going in opposite directions, then if you looked at it one way, it would be a particle, and if you looked at it another way, it would be a wave, but it would never occur to you to think that they're two aspects of the same thing because they're going in opposite directions. Surprisingly, none of the founders of quantum mechanics, Einstein, Bohr, Schrödinger, Heisenberg, Dirac, Feynman, none of them ever asked in which direction do the waves go. Without debate and without empirical evidence, it was considered obvious that waves and particles travel in the same direction, and upon that foundation, quantum mechanics was built. Perhaps the best explanation of the double slit experiment can be found on YouTube, a discussion by Dr. Quantum, who is a cartoon character. He considers every conceivable explanation of what happens in that experiment and cannot explain it, and ends up saying, "What the bleep do we know?" But Dr. Quantum never considers the obvious possibility that the waves are going in the opposite direction as the particles. It never crosses his radar screen. What I'm about to tell you in this video comes primarily from 2 of my teachers, one of whom I've never met, James J. Binney, who teaches the subject at Oxford University, and you can find his 27 introductory lectures on YouTube and iTunes, and the price is right, $0. I've downloaded all of Binney's lectures into my iPhone. My other teacher is somebody that I know well, named Louis E. Little. It turns out that he and I are cousins. We grew up together in northern New Jersey, and so he has taught me his theory of elementary waves, or TEW. Now, I'm going to break this into 2 parts. Introductory TEW, which I will call E1, not his term, and advanced TEW, which I will call E2. In the video you have embarked on looking at, there is unfortunately some mathematics. Now I know that many, perhaps most in the audience, are phobic and avoidant of mathematics. I can tell you that there isn't much mathematics. It soon comes to an end, and if you can just kind of sit through it, it will go away, and then you will find a video which is almost like a sci-fi movie in which you will ask of me, is this guy psychotic? Many people might think that Binney and Little say contradictory things, but I don't think so. Binney lives on your side of the video screen, whereas Little lives on my side, and therefore they complement each other and do not contradict each other. Think of it this way. How can a person living in one universe contradict a person living in another universe? That's what we're dealing with here. A schizophrenic guy who has conceived of there being two universes that interface right here at your video screen. The fact that I have an iPhone that works on my side of the video screen means that in the absence of wave-particle duality, quantum technology works just fine. The theory of elementary waves is the primary software running on my side of the video screen. It's what makes the world organized at all. Whereas quantum mechanics is the primary operating system on your side of the video screen. This is a double-slit experiment with an electron gun, a barrier screen in the middle with two slits, S and T, and a target screen. Electrons spray out of the gun. Some of them go through the two slits and spray over and are detected at the target screen. As an electron comes out of the gun, it has a certain momentum, small p, and it maintains that momentum even when it passes through one of the slits, although its direction might be slightly deflected. The question we're interested in is what is the probability of an electron being seen at point X near the center of the target screen. Now at point X, let A sub S be the amplitude for the electron having come through slit S, and AT being the amplitude for it coming through T. So the probability of an electron being seen at X is the mod squared of amplitude AS and amplitude AT, and those two are complex numbers. When we square this out, we get this term, the left two parts of which are the classical probability that an electron will have come through slit S or slit T, and the right-hand two terms of which are quantum interference terms. We can simplify the quantum interference by recognizing that AS can be viewed as having a modulus and a phase. The phase is e to the I phi s. Therefore, the probability of an electron being seen at point X near the center of the target screen is this. And you'll notice there in the quantum interference part of it, there's a cosine of phi s minus phi t. That's the key. That's what I want to focus on. And because there's a cosine, that explains why, as X moves up and down the target screen, you get a sinusoidal curve. I have, of course, skipped over most of the details. What I've been discussing about quantum interference is predicated on the idea of a wave particle or a wave packet moving in this direction. But that's only true on your side of the video screen. On my side of the video screen, it's different. Over here, you have a wave without a particle moving in this direction, and an electron then follows the wave backwards. Now I'm going to propose that the quantum interference that took place over here on your side of the video screen, on my side of the video screen, takes place over here at the electron gun, and that there is symmetry. It's the same interference. An electron arriving at point X on the target screen can have come through either of two pathways, ds or dt, and dt is slightly longer than ds because x is not on the midline. Now the difference, dt minus ds, is why you get a phase difference, phi s minus phi t, the cosine of which is the key to understanding the pattern on the target screen. Now let's say that this is the wave that comes through slit S, and this is the wave that comes through slit T, and they converge at point X. What the variable phi S refers to is the phase of the wave, whether you're here or here or here on this wave. The difference phi S minus phi T refers to two waves as they arrive at the target screen, the difference in phase between phi T up here and phi S down there. Now, where they converge, if we move X slightly up and down the target screen, then we change the distance dt relative to ds, resulting in a shift like this of one wave versus the other, because they're both going at the same speed, but this one has further to go. When you cross from your side to my side of the video screen, waves go in the opposite direction, as I said before. Now on this video I am calling this E1, which is my own name for the introductory part of the theory of elementary waves. Now you are going to ask, how can, even on my side of the video screen, how can rays come out of the target screen? Well, according to the E1 view of reality, there are waves and rays of all wavelengths going in all directions all the time. Only when an electron is involved with them can we know anything about them. These elementary rays do no work. They don't push or pull an electron, but they do provide the pathway that an electron will follow backwards. Now, if you look at this diagram and imagine rays converging on the electron gun from three different points on the target screen, shown in yellow, red, and blue, I claim that they will have different amount of quantum interference at the electron gun, and that magnitude of quantum interference at the electron gun will precisely match the same quantum interference that would have existed at the target screen had the waves been going in the other direction. If, in the conventional interpretation of the double slit experiment, the waves start over there at the electron gun, they start in phase because they're two aspects of the same wave. They go through slots S and T, and depending on how much dt is longer than ds, they arrive some amount out of phase, which determines the phase difference. Now, if the same waves are going in the opposite direction, then they start at point X over there in phase because they're two aspects of the same wave. They go through slits S and T, and they arrive out of phase the same amount determined by the length that dt is longer than ds. So whether the waves are going in that direction or that direction, the dt minus ds number is that which determines the phase difference. Thus you get the same quantum interference at the electron gun as you would have at the target screen, depending on the direction of the waves. Now let's look at it from an electron's point of view. On our side of the video screen, an electron cannot move on its own. It must follow an elementary ray. So it's waiting for all these impinging rays coming at it from all the different points on the target screen, and it must choose which one to respond to. The probability of an electron latching onto and responding to one of these impinging waves is proportional to the intensity of the wave as it comes in, which is dependent on the quantum interference. If an electron does fire at random among one of these different impinging elementary rays, it will follow that ray and that ray alone, backwards with a probability of 1 through one and only one slit to precisely that point on the target screen from which its ray came. Thus, the electron will have a trajectory. All the quantum interference will have occurred, all the probabilities will have occurred and been finished prior to the electron being fired. And thus, if it has a trajectory, there's no need for the concept of wave function collapse and no market for a many worlds theory. Those of us who live on this side of the video screen find that the double slit experiment comes out the same on our side as it used to on your side when we lived over there. The same probability of dots appearing at the same places on the target screen appears on our side as on your side. Now, I've been living on this side of the video screen for quite a while and in this world of E1, and I'm going to share with you a fantasy that I have of what these elementary waves might look like. I think of the elementary rays as being helical, like a corkscrew in pattern. As you can see, a helix has a direction, it has an amplitude, which is the diameter of the helix, and it has a phase, which I am symbolizing by this clock face. The clock face is meant to be a unit vector in a complex plane. The model I'm discussing on our side of the video screen, E1, has nothing in common with the Wheeler-Feynman time reverse model. Time may go backwards or forwards in the mind of a mathematician, but in the life of human beings, which is what I am actually, even though I live over here, only goes in one direction. And therefore, our waves also have nothing in common with time reversal waves. Time only goes forwards on this side of the video screen. Furthermore, what I'm about to say has nothing in common with a pilot wave theory. We come now to E2, the more advanced form of the theory of elementary waves taught to me by Louis Little. If you think about E1, there are some problems with it. For example, if waves go in all directions, then they might as well go in the same direction as the electron. Why not think of a wave that comes out through the electron gun, goes through one of the two slits and hits the target screen where there is interference, and then an electron follows such a wave as that. Now these would differ from the usual quantum mechanics waves in that quantum mechanics waves do not exist until an electron exists and is fired, whereas these waves are there all along. Another key difference between elementary waves and quantum waves is that elementary waves are thought of as being real as my skull. They exist in reality, although they may be studied mathematically, they are not basically founded in mathematics. By contrast, quantum waves are mathematical fictions or mathematical objects. They are probability waves or probability densities. When we compare elementary waves to quantum waves, there is a final difference which no one can argue with, which is that quantum waves exist on your side of the video screen and don't exist on our side, whereas elementary rays exist on our side. So this brings us to the more advanced form of E2, in which elementary waves go in both directions, coaxially, and an electron somehow follows this railroad track. The probability of an electron following a pair of elementary rays is proportional to the amplitude of one ray times the amplitude of another ray. Now you might think, jeepers, that's complicated. Is there any empirical data supporting it? And in fact, there is compelling empirical data. Quantum mechanics experts cannot tell you Not only can they not tell you what happens during wave function collapse, they can also not tell you why quantum amplitudes are squared to get probabilities. It must say something about nature, but what? And here's a possible answer. What it says is that there are two mirror images of waves, one going with the particle, the other going opposite to the particle, to find out the probability of an electron following this railroad track of two different waves going coaxially in different directions. You multiply the amplitude of one wave times the amplitude of the other, you don't square anything. Now, I know that it is probably very hard for viewers to comprehend what on earth I'm talking about, because what I'm talking about is a huge paradigm shift. If you thought about it, it would mean that we live in a very different world than most people think we live in. So, what can we say about a paradigm shift of this magnitude? Well, I could say this. In about an hour, I'm going to the hospital to work as a psychiatrist, and there I face paradigm shifts greater than this. For example, there is a man that I treated who was so paranoid that he lived in a cardboard box in the back alley of the city. And one winter during a blizzard, it got so cold that he acquired frostbite. After that, they referred him from the surgical floor to the psychiatry floor where I treated him. Now, I listened to him and I tried to understand his point of view, which was quite a paradigm shift. As a matter of fact, I never did really understand. I asked him, what is it like living in a cardboard box in the back alley? And he said, I live like a king. Eating meals out of dumpsters is the finest food available. It made no sense to me, but I listened to him and tried to relate to him. And I said some things to him which he didn't like, such as, you know, whether you like it or not, you have to take this medicine. Now, I know you think there's nothing wrong with you and that everybody else who's persecuting you are the ones who are crazy. But you must take this medicine even though you don't think you have any illness. And furthermore, the authorities who run this city are unfortunately not going to allow you to go back and live in your cardboard box again. The final section of this video, the part you've been waiting for, is my explanation of why on this side of the video screen we find that wave-particle duality is false, we don't have it, and we don't miss it. Our quantum technology, like my iPhone, works just fine without wave-particle duality. So, what's going on? It is generally thought on your side of the video screen that wave-particle duality cannot be challenged because it is supported by, it rests upon a vast mountain of empirical data. But on my side of the video screen, that mountain of evidence looks quite different. Let's consider only one experiment, which is called the Davison-Germer experiment, done in the 1920s in the Bell Labs of New Jersey. Now, these guys fired electrons at a nickel crystal, expecting that the electrons would bounce off the crystal like ping pong balls. And most of the time, the electrons did bounce off. And if the electrons bounce off, then the data would follow this curve that you see before you, because this curve is the data, the actual data from Davison and Germer. However, under certain very specialized circumstances, something unusual happened in the data. It developed this horn you see here at 50 degrees. That horn cannot be explained by electrons bouncing off like ping pong balls. It turns out the only way to explain this horn is if there are waves refracting through the crystal. So what did Davison and Germer prove? Well, obviously they proved that there are electrons present and there are waves present in their experiment. Now, every textbook of physics says that Davison and Germer proved wave-particle duality, but that is an overstatement. What Davison and Germer proved is that there are waves and that there are particles and they interact. So what are some other possible ways in which waves and particles might interact? Well, there's E1 and E2. So what the textbooks of physics should say but do not say is that wave-particle duality was proved by Davison and Germer to be one of the ways in which waves and particles might interact. So now I've sketched out some of the reasons why, on my side of the video screen, wave-particle duality is false. I know it's true on your side of the video screen, we're not talking about that. But as a matter of fact, I don't think it is useful to talk about whether wave-particle duality is true or false. Wave-particle duality is simply a signal as to which operating system you are using. To run the world, you need an operating system. On your side of the video screen, that operating system is quantum mechanics. On my side, it is E1 and E2. Now, if you use QM as your operating system, then it is obvious that wave-particle duality is true. If, on the other hand, you use E1 and E2 as your operating systems, then it is obvious that wave-particle duality cannot possibly be true. Now, these two operating systems are as different as Windows versus Mac. If you were comparing Windows and Mac, you would not say, well, is one true and the other false? That's not a useful way to think. You would say, one has advantages for some purposes, the other has advantages for other purposes. And that's how I propose to think about the difference between your side and my side of the video screen. If you are going to run a business, I would recommend a Windows environment. If you're going to make a home movie for YouTube, I would prefer to use a Mac environment. If you're going to try to solve technological problems, there's nothing better than QM, and its strengths and accomplishments are so well known, I'm not even going to mention them. So what are the advantages of E1 and E2? They're taught in no universities. You can really only find them on this side of the video screen, and this over here, this is an imaginary space. They have yet to solve a single engineering problem. They have never designed a cell phone or a laser. So what is the advantage? Well, the advantage in my mind is that they are quirky and peculiar and the kind of thing a person like me would take an interest in. As a psychiatrist, I'm not too much troubled by weirdness. But there are those who are very troubled by quantum weirdness, who point out that the weirdness of this operating system does not reflect reality. It reflects the idea that there's something wrong with this operating system. That which is wrong is symbolized by my finger being askew ever since I had a bicycle accident. The primary motivation for trying to develop a new operating system on this side of the video screen is to find an operating system that more closely reflects what is actually happening in nature. And you can already see this embedded in the fact that this operating system can explain, whereas this operating system cannot explain why we square the amplitudes to get probabilities or what happens during wave function collapse. Thank you very much for your time and attention.